All right, we're going to look at the volume. We're going to find the volume of the region bounded by the paraboloid. English is hard. Paraboloid z equals 9 minus x squared minus y squared above and below a unit circle in the xy plane. Now, your book, again, I'll start with drawing, but your book goes to writing this in Cartesian coordinates because this is in Cartesian coordinates. I immediately with the unit circle would go to writing it in I would immediately go from because of the unit circle on it, writing it in cylindrical coordinates. All right, let's see if that gives me a good, yeah, there's my xy plane. So we have a boundary up here, and then we're going to have a unit circle as our bounding point. I don't know how to oblate a circle well, but we'll look at this as being our boundary. And then in the surface up above here, so when this is 0, this is up at 9. All right, and then when we're here on the unit circle, that's 0 and 1, so that's going to be up at 8. Well, let's get and when this is up at 8, this is up at 8, and this is up at 8. And so we're kind of looking at this curves down, right? Curves down to here, curves down to here, and has a circular framing here. Well, we have this cap over top of, and this paraboloid is capped here with this cylinder coming up. And this does seem to be centered around the origin, so this has a very symmetric form to it. And so we want to find the volume that is expressed by this. Again, I think this is well suited for the symmetries of a unit circle, because we're going to go from 0 to 2 pi to get all the way across it, and we're going to go from 0 to 1 for r. So what we need to do is we need to rewrite this in terms of polar coordinates. And I guess what we want to note is r equals x squared plus y squared, x equals r cosine theta, y equals r sine theta, and if we ever need it, the inverse tangent of y over x is where we get theta from, right? These are relationships that will help us kind of routinely go back and forth. Well, if you look at this, this is 9 minus r. 9 minus r x squared plus, oh wait, x squared plus y squared square root. Sorry, forgot that in there, right? It's my vectors, and so this is r squared here. Because if I square this, I get x squared minus y squared, right? So if we see this portion here, if I take that out, that's going to be x squared plus y squared, which is r squared. And so this whole thing is 9 minus r squared, which starts to look a little bit prettier. in polar coordinates, because now I will do my area element as r dr d theta. And this then works nicely. I'm just going to 9r minus r cubed dr d theta. And now I'll do my first integration. So that's going to be 9r squared over 2 minus r to the 4th over 4, evaluated from 0 to 1. I'll ignore the zeros because I'll be subtracting zeros, so that's 9 halves minus 1/4 d theta, evaluated from 0 to 2 pi. Notice there's no variable for theta here, so this is a number. So I think this is 18/4 minus 1, or 17/4. So I'll just bring that out front. D theta, which is 17/4 theta, evaluated from 0 to 2 pi, or 17 over 2 times pi. And we found the area of our or our volume of our solid. So polar coordinates really work nicely when we have polar symmetries.